Now, in this lecture, we'll find out the radius of the small circle. In the drawing, we have this small circle that is inscribed by a semicircle. We know that side CD equals to 3 units, side DB equals to 4 units, angle CDB, this angle equals to 90 degrees, and we want to find out the radius of this small circle. So first of all, we will do a construction. We will complete the semicircle to a circle. So we completed the semicircle to a circle. In the next step, we will extend line segment CD by a straight line until it touches the circle. And we will define the touching point of the extended line segment CD, and the circle is point E. Point E is the touching point of the extended line segment CD into this circle. Okay, and here actually we extended the straight line CD by a straight line, and when you extend a straight line by a straight line, the result must be a straight line. So therefore CE, that is the result of the extension of CD by a straight line, CE must be also a straight line. So I can write down here that CE, line segment CE, is a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles here must be equal to 180 degrees. So at point D, on this side of the straight line C at point D, which angles we have? We have here one angle that is equal to 90 degrees plus angle EDB. So 90 degrees plus the size of angle EDB. In total, the sum of those two angles must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So 90 degrees plus angle EDB equals to 180 degrees. We subtract 90 degrees from this equation, and we get that angle EDB, the missing angle EDB equals to 180 degrees minus 90 degrees, it is 90 degrees. So we actually found out that this angle is a right angle, it is equal to 90 degrees. Okay. So we actually know that angle CDB, this angle equals to 90 degrees, and angle EDB also equals to 90 degrees. And when we extended the semicircle, when we created from the semicircle a circle, we actually created a second semicircle. So this semicircle that we created is a mirror image of the original semicircle. Again, this semicircle is a mirror image of the original semicircle, and likewise, when we extended the 9 segment CD by a straight line, so this angle equals to 90 degrees, and this angle also equals to 90 degrees. Actually, DE, 9 segment DE, is the mirror image of CD. And because of the fact that DE is the mirror image of CD, DE must be equal to CD in its length, but it is in the opposite direction. So we can write down that CD equals to DE, because of the fact that DE is the mirror image of CD. Both line segments are equal to each other in their length, but they are in the opposite directions. We have here point D is a common point to those both line segments, and line segment DC is in the direction of the upwards, while line segment DE is in the direction of downwards, but their lengths are equal to each other. So CD equals to DE by symmetry. By symmetry, I repeat again, DE is the mirror image of CD, therefore they are equal to each other in their lengths, and they are in the opposite direction in relation to to each other. Okay, so CD equals to DE, and we know that CD equals to 3 units. CD equals to 3 units, and from these equations 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. DE equals to 3 units. Okay, here we can write down that DE equals to 3 units. So, in the next step, I will present to you a new rule that is actually rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So here we have, this is chord AB that intersects with chord CD. It's point O. I repeat again, point O is the intersection point of chord AB with chord CD. Then AO times OB equals to CO times OD. I repeat again. If chord AB, this is chord AB, intersects with chord CD, the red line is called CD. It's point O. Point O is the intersection point of chord AB with chord CD. Then, according to rule number 1, we will get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule number 1 in our drawing, because in our drawing we have chord AB. This is chord AB that intersects with chord CE. We have chord AB intersects with chord CE at point D. Chord AB, this is chord AB, intersects with chord CE. This is chord CE at point D. At this point D is the intersection point of chord AB with chord CE. I'll repeat again. Chord AB intersects with chord CE at point D. Therefore, according to rule number 1, we get that AD times DB equals to CD times DE. Repeat again. AD times DB equals to CD times DE according to rule number 1. AD times DB equals to CD times DE according to rule number 1. So here, AD is the missing line segment, so we leave it as it is, times DB. DB equals to 4 units according to what is given us in the question, so we'll substitute DB by 4. And it is equal to CD. CD equals to 3 units. Times DE. DE also equals to 3 units according to what we already found out. So in conclusion, according to rule number 1, we actually found out that AD times 4 equals to 3 times 3. 3 times 3 is 9, so in conclusion, we found out that 4 times AD equals to 9. Here we'll divide this equation by 4, and we'll get that AD, the missing line segment AD, equals to 9 over 4 units. So here, the missing line segment AD equals to 9 over 4 units. So here, AB is the diameter of the semicircles and also the diameter of the circle. And we know that the diameter of any circle or semicircle is twice as long as the radius. Okay, so actually, if we divide the diameter AB by 2, we'll get the radius of this semicircle and the circles itself, or the circle itself. So we define the radius of this circle and the semicircles as capital R, and we will get that capital R equals to AB, that is the diameter over 2. From the drawing we can see that AB equals to AD, that is 9 over 4 units. AD plus DB. Again, we'll substitute AD by AD plus DB. Okay, AB, from the drawing you can see that AB equals to AD plus DB, so we'll substitute AB by AD plus DB divided by 2. We have already found out that AD equals to 9 over 4 units. So we substitute AD by 9 over 4 and DB equals to 4. We'll substitute DB by 4 or divided by 2. So here 9 over 4 plus 4, we have 9 over 4 plus 4. So we'll multiply 4 by 4 and then we'll divide it by 4 in order to have a common factor with 9 over 4. And we'll get that 9 plus 4 times 4 is 16 over 4 over 2. 9 plus 16 is 25 over 4. And here we'll move 2 to the denominator and we get that capital R equals to 25 over 4 times 2. 4 times 2 is 8, so in the denominator we have 8. So in conclusion, we actually found out that the radius of the circle and the semicircles, it is equal to 25 over 8 units. Okay. So in the next step, we will define the center of this circle as point P. This is the center of the circle, big circle, and the semicircles, and we'll define the center of this small circle as point Q. Point Q is the center of this small circle, and we will find out the length of the short line segment DP. What is the length of line segment DP? From the drawing, it is very easy to see that DP equals to DB minus PB. I'll repeat again. The short line segment DP equals to its length to DB minus PB. Okay. Here DB equals to 4 units according to what is given as the question, so we'll substitute DB by 4. And what is the length of line segment PB? P is the center of the big circle. B is a point on the big circle itself. This is exactly the definition of a radius. That is to say, PB is the radius of the big circle that is equal to capital R according to our definition. So in conclusion, we found out that dP equals to 4 minus capital R. But we have already found out that capital R equals to 25 over 8 here. So we can substitute capital R by 25 over 8. We'll do it now. We'll get that dP equals to 4 minus capital R is 25 over 8. Here we have 4 minus 25 over 8. So we will multiply 4 by 8 and then we will divide it by 8 in order to have a common factor with 25 over 8. And we get here that dP equals to 4 times 8 is 32 minus 25 over 8. 32 minus 25 is 7. In the denominator we have 8. So in conclusion, we found out that the short line segment DP, it is equal to 7/8. Okay, DP equals to 7/8. So we can write here that DP equals to 7/8 in its length. 7/8 units. Okay. In the next step, we will define the point of tendency of tangent DB. Here, tangent DB with this small circle as point M. Again, this point M, is the point of tendency of tangent DB with this small circle. And we will also define the point of tendency of tangent CD with this small circle as point O. Point O is the point of tendency of tangent CD with this small circle. And in the next step, we will join points Q and O together by a straight line. What is the definition of line segment QO? Q is the center of the small circle. O is the point on the small circle itself. This is exactly the definition of a radius. That is to say, QO is the radius of the small circle, so we will define the radius of the small circle as r, small r. So QO is the radius of the small circle, that is equal to small r, according to our definition. So here, the radius QO of this small circle, it is drawn to the point of tendency, that is to say, it is drawn to point O, that is the point of tendency of tangent DC with this small circle, and whenever you have a radius that is drawn to the point of tendency, like in this drawing, then the tangent CD, this tangent CD will be perpendicular to the radius OQ. So CD is perpendicular to OQ. If CD is perpendicular to OQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points Q and M together by a straight line. So Q is the center of the small circle. M is the point on the small circle itself. This is exactly the definition of a radius. That is to say, QM is the radius of the small circle that is equal to small r according to our definition. So here we have QM. The radius QM, it is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. So if DB is perpendicular to MQ, again DB is perpendicular to MQ. It means that this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So actually, if we focus on quadrilateral OQDM, this quadrilateral OQDM, in quadrilateral OQDM, we have 1, 2, 3 right angles. Again, in quadrilateral OQDM, we have 1, 2, 3 right angles. So I write it down. In quadrilateral OQDM, we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually this angle OQM. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we will subtract 270 degrees from this equation, and we will get that the missing angle, angle OQM, equals to 360 degrees minus 270 degrees. It is equal to 90 degrees. So angle OQM, it is the right angle, it is equal to 90 degrees. So you can write here that angle OQM equals to 90 degrees. Actually, in quadrilateral OQDM, we have 4 right angles. Okay, any quadrilateral that has 4 right angles must be at least a rectangle. So we will relate to quadrilateral OQDM as a rectangle. Quadrilateral OQDM is a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, OQ equals to DM. OQ equals to DM, according to the rule that the opposite sides of a rectangle are equal to each other. OQ must be equal to DM in rectangle OQDM. But OQ equals to small r, according to what we have already found out. OQ equals to small r. So we can write here that OQ equals to small r. And from this equation, r equals to OQ equals to dm, we will derive that dm is also equals to r. dm is also equal to small r. So here, dm equals to small r. Okay. What is the length of line segment PM? The length of line segment PM, from the drawing, it is very easy to see that the length of line segment PM, it is equal to dm minus dp. Again, dm minus dp equals to pm. Very easy to see from the drawing. pm equals to dm minus dp. So pm equals to dm. dm equals to r, according to what we just right now found out, that it is equal to small r, so we substitute dm by small r minus dp. dp equals to 7/8, according to what we have already found out. So in conclusion, we found out that PM equals to r minus 7/8. Okay. Here, this point is the point that the two circles touch each other. Okay, this is actually the point of tendency between the small circle and the big circle. It is the touching point of the small circle with the big circle. So we define this point as point S, and we can define point S also as the launch point. Point S is the launch point of the small circle with the big circle. Okay, point S is the launch point of the small circle with the big circle. And because of the fact that the small circle is located inside the big circle, this launch point is an internal launch point. Okay, so point S is an internal launch point, I'll write it here that point S is an internal launch point. So actually in this drawing we have an internal launch point of the big circle with the small circle. Okay? Those two circles are touching each other internally at point S. Therefore, in this drawing we have an internal launch point of the small circle with the big circle. Okay? So, in the next step I will present to you a new rule that is related to internal launch point. Rule number 2. According to rule number 2, if two circles have an internal launch point between them, have an internal launch point between them, then the straight line that connects their centers the straight line that connects their centers passes through the launch point of the two circles. So I'll write rule number 2 again. According to rule number 2, if two circles have an internal launch point between them, then the straight line that connects their centers passes through the launch point of the two circles. So actually, according to rule number 2, as I already explained to you, those two circles have internal launch point between them. That is to say, they are touching each other internally at point S. So we can implement rule number 2 in our drawing. And according to rule number 2, the straight line that connects their centers, point P is the center of the big circle, point Q is the center of the small circle, and the straight line that connects their centers together is PQ. So the straight line PQ passes through the launch point. That is to say, the straight line PQ passes through the launch point that is actually point S. Okay? So here, the straight line PQ passes through point S. Okay, the straight line PQ passes through point S, that is the launch point. So that is to say, according to rule number 2, points P, Q, and S they are all located on the same straight line. So I know that according to rule number 2, points P, Q, and S they are all located on the same straight line. Points P, Q, and S they are all located on the same straight line. I repeat again on the conclusion. From rule number 2, we can conclude that points P, Q, and S they are all located on the same straight line. Why? Because the straight line PQ that connects their centers together passes also through point S. That is to say points P, Q, and S they are all located on the same straight line. Or we can express it differently that line segment PQS is a straight line. Okay, you can also write down that line segment PQS is a straight line. I repeat again on our conclusion. The second conclusion that is actually very similar to the first conclusion, that PQS is one straight line. Line segment PQS is one straight line. So here, what is the length of line segment QS? Here, Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. That is to say, QS will be the radius of the small circle that is actually equal to small r. And what is the length of line segment PS? The red line segment PS. Point P is the center of the big circle. Point S is a point on the big circle itself. This is exactly the definition of a radius. So PS, line segment PS is the radius of the big circle, that is to say it is equal to capital R. But we have already found out that capital R equals to 25/8. So in conclusion, we found out that PS equals to capital R and it is equal to 25/8 units. And what is the length of line segment PQ? The length of line segment PQ from the drawing, it is very easy to see that the length of this line segment PQ, it is equal to PS minus QS. PS, the red line, minus QS is equal to PQ. I'll repeat again. PQ equals to PS minus QS. But we have already found out that PS equals to capital R and QS equals to small r. So in conclusion, we found out that the length of line segment PQ equals to capital R minus small r. But we have already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. So PQ, in conclusion, PQ equals to 25 over 8 minus small r. Okay, PQ equals to 25 over 8 minus small r. So we can write here that PQ this line segment PQ equals to 25 over 8 minus small r. And we have already found out that PM equals to small r minus 7/8. And we found out also that QM equals to small r. So actually, I will copy the right triangle QPM in a new page, and we will implement the Pythagoras theorem on this right triangle QPM. The only missing variable in this triangle is small r. That is actually that is what we are looking for in this lecture. We want to find out the radius of the small circle that is actually equal to small r according to our definition. So I'll copy the right green triangle QPM in a new page, and we will implement the Pythagoras theorem on the green right triangle QPM. Okay. So this is the right triangle QPM that I copied from the original drawing. We have already found out that QP, the hypotenuse QP, equals to 25 over 8 minus small r. We already found out that PM equals to small r minus 7/8. And QM equals to small r. So in the right triangle QPM, by PT is a abbreviation for Pythagoras theorem. We get that according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ and the square of the hypotenuse is PQ squared. And it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to QM squared plus PM squared. Okay? According to the Pythagoras theorem, PQ squared equals to QM squared plus PM squared. We substitute PQ by 25 over 8 minus r. So PQ squared will be equal to 25 over 8 minus r squared. And it is equal to QM squared. QM equals to small r, so QM squared is small r squared plus PM. PM equals to small r minus 7/8. So actually PM squared will be equal to small r minus 7/8 squared. So here we will open the brackets on both sides of equation number 1, and we will get that according to equation number 1, 25 over 8 minus r squared. It is equal to, according to the algebraic identity, that a minus b squared equals to a squared plus b squared minus 2 times ab. We will get that 25 over 8 minus r squared equals to 25 over 8 squared. That is 25 squared is 625 over 8 squared. This is 64 plus r squared minus 2 times 25 over 8 times r. And the other side of equation number 1, we have r squared plus r minus 7/8 squared is r squared plus 7/8 squared, that is 7 squared is 49 over 8 squared is 64 minus 2 times r times 7/8. So here we have r squared on both sides of the equation. So r squared will get cancelled. What is left from equation number 1 after we cancel r squared? We have here 625 over 64 we have this expression equals to minus 2 times 25r over 8. We will divide both the numerator and the denominator by 2. Minus 2 over 2 is minus 1, so minus 2 will get cancelled, and we left in the numerator only with minus 25r. In the denominator we have 8 that is divided by 2, it is equal to 4. So in conclusion, this expression equals to minus 25r over 4. And in the other side of equation number 1, we have r squared plus 49 over 64. Here we have the expression of minus 2r times 7 over 8. We divide both the numerator and the denominator of this expression by 2. Minus 2 over 2 is minus 1, so minus 2 will get cancelled. And we left in the numerator only with minus 7r over 8 that is divided by 2, it is equal to 4. So this expression in conclusion equals to minus 7r over 4. Here we will multiply this equation number 1 by 64, and we will get here that 625 times 64 over 64 equals to 625. And here we have 64 minus 64 over 4 is minus 16 times 25r. So in conclusion, this expression minus 25r over 4, after we multiply it by 64, it is equal to minus 16 times 25r. In the other side of the equation, we have r squared plus 64 is 64r squared. And we also have here 64 times 49 over 64 is 49. And we have here minus 7r over 4 multiplied by 64. So it is minus 64 over 4 is minus 16 times 7r. So in conclusion, this expression minus 7r over 4 after we multiply it by 64, it is equal to minus 16 times 7r. So here, according to equation number 1, 625 minus 16 times 25 is minus 400r. And it is equal to 64r squared plus 49 minus 16 times 7r is minus 112r. So here we will add 400R to this equation number 1. And we will get that 625. Here we have 400R minus 400R is 0, so in this side of the equation number 1 we left only 625. That is equals to 664R squared plus 49. And we have here 400R minus 112R is plus 288R. Okay, so here we subtract from this equation number 1, 625, and we get here that 625 minus 625 is 0, and it is equal to 64R squared plus 288R, and we have here 49 minus 625 equals to minus 576. So according to equation number 1, we got that 0 equals to 64R squared plus 288R minus 576. So we divide this equation number 1 by 32, and we get that according to equation number 1, 64 over 32 is 2. So this expression in total equals to 2R squared. And we have 288R over 32 is 9R. Minus 576 over 32 is minus 18. That is equal to 0 over 32 is 0. So in conclusion, we got the quadratic equation that 2R squared plus 9R minus 18 equals to 0. So in this quadratic equation, the coefficient A equals to 2, the coefficient A equals to 2, the coefficient B equals to 9, and the coefficient C equals to minus 18, and the variable that we are looking for in this quadratic equation is R, small r, that is to say x equals to small r. Okay. And the general formula for solving out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is r, so we'll substitute x by r. And we will put the data inside the equation in order to find out the value of the values of r. So r equals to here minus b, b equals to 9, so minus b is minus 9, plus minus square root of b squared. B equals to 9, so b squared is 9 squared, that is 81. Minus 4 times a is 2, times c is minus 18. All divided by 2a. A is 2, so 2a is 2 times 2, that is 4. So here we found out that R, the radius of the small circle, equals to minus 9 plus minus 81. We have here minus 4 times 2 is minus 8. Minus 8 times minus 18 is plus 144. So inside the root we have 81 plus 144, all divided by 4. So here we found out that R, the radius of the small circle, is equal to minus 9 plus minus 81 plus 144 is 225, so inside the root we left only with 225 divided by 4. So here we found out that R, the radius of the small circle, equals to minus 9 plus minus square root of 225 is 15 over 4. So here we will have two solutions that are possible for R. The first solution for R is that R equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 9. So we found out that R, the radius of the small circle, equals to minus 6, that is a negative number. Okay, but because of the fact that according to our definition, R is the length of the radius of the small circle, so R is the length of the radius of the small circle. So R is a length, it must be a positive number. R is a length, and R is a length, it must be a positive number. So it can never be equal to minus 6, that is a negative number. So we cancel the solution, and we left only with the second solution, that R equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and 6 over 4. Here R equals to 6 over 4. We will divide both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that R, the radius of the small circle, equals to 3/2 units. It is R equals to 3/2 units, or in terms of numbers, it is equal to 1.5 units. This is the answer to the question. I will repeat again. R, the radius of this small circle, it is equal to either 3/2 units, or in terms of numbers, it is equal to 1.5 units. In the next step, I will summarize the lecture. Actually, we wanted to find out the radius of this small circle. It has been given to us that side CD, we have here a circle that is inscribed by a semicircle. Okay, line segment CD equals to 4 units, line segment DB equals to 4 units. This angle CDB equals to 90 degrees, and we want to find out the radius of this small circle. So in order to find out the radius of the small circle, we did a construction. We completed the semicircle to a circle, and by completing the semicircle to a circle, we created a second semicircle. This is the second semicircle that we created. That is actually the mirror image of the original semicircle, this original semicircle. So this semicircle is a mirror image of the original semicircle. And in the next step, we extended straight line CD, line segment CD by straight line until it touches the circle at point E. Point E is the touching point of the extended line segment CD with this circle. Okay? And actually, we extended the straight line CD by straight line. and when you extend a straight line by a straight line, the result must be also a straight line. That is to say, we extended the straight line CD by a straight line and we got line segment CE. The result of extending the extension of line segment CD by a straight line is a line segment CE. So the result must be also a straight line. That is to say, CE is a straight line. Okay, CE is a straight line because when you extend the straight line by a straight line, the result must be a straight line. And then I presented to you the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on this side of the straight line C at point D, then the sum of the angles here must be equal to 180 degrees. So which angles we have here? We have here 90 degrees plus angle EDB. So at point D, 90 degrees plus angle EDB equals to 180 degrees according to the rule that the sum of the angles the sum of the angles on one side of a straight line is equal to 180 degrees. Here we subtracted 90 degrees from this equation and found out that the missing angle EDB equals to 90 degrees. Here this angle equals to 90 degrees. So actually here we have angle CDB, this angle equals to 90 degrees, and angle EDB, this angle is also equals to 90 degrees. Okay, and so when we extended line segment CD by a straight line, we actually created the mirror image of line segment CD. That is to say, DE is the mirror image of CD, and because of the fact that DE is the mirror image of CD, it means that both line segments, they are equal to each other in their lengths, and the only difference between those two line segments is they are in opposite directions. They have the common point, point D, and they are in the opposite directions, but they are equal in their lengths. So you can write down that CD equals to DE because DE is the mirror image of CD. So CD equals to DE by symmetry. And here we know that it is given us in the question that CD equals to 3 units. So we can write here that CD equals to 3 units. And from this equation 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Here, DE is also equals to 3 units. Then I presented to you rule number 1. According to rule number 1, if chord AB intersects with chord CD at point O, then AO times OB equals to CO times OD. So we have this circle. Inside this circle, I should emphasize that here the intersection point is inside the circle. Okay, point O, that is the intersection point of chord AB with chord CD, is occurring inside the circle. Okay, so if chord AB intersects with chord CD at point O, I will add to it inside the circle. So if chord AB intersects with chord CD inside the circle at point O, then according to rule number 1, we get that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD, according to rule number 1. So we actually can implement rule number 1 in our drawing. Well, because in our drawing, we have chord AB. This is chord AB intersects with chord CE. This is chord CE, it's point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number, repeat here again, chord AB intersects with chord CE at point D. Point D is the intersection point of chord AB with chord CE. Therefore, according to rule number 1, we will get that AD times DB equals to CD times DE. Again, AD times DB equals to CD times DE. Here, AD times DB equals to CD times DE according to rule number 1. AD is the missing line segment, so we leave it as it is. DB equals to 4 units according to what is given us in the question. CD equals to 3 units also according to what is given us in the question. DE, we've already found out that DE is also equals to 3 units. So in conclusion, we found out that AD times 4 equals to 3 times 3. 3 times 3 is 9, so in conclusion, we found out that 4 times AD equals to 9. We divided this equation by 4, and we found out that AD equals to 9 over 4. So this line segment, the missing line segment AD, equals to 9 over 4. And we also know that AD is the diameter of this circle, the big circle, and also the diameter of the semicircles. And we know that the diameter is twice as long as the radius. So if we divide the diameter AB by 2, we'll get the radius. Okay? So we divided the diameter AB by 2, and we get the radius, according to our definition, the radius of the big circle and also the radius of the semicircles. They are defined as capital R. So capital R equals to the diameter that is AB over 2. From the drawing, you can see that AB equals to AD plus DB. So we substituted AB by AD plus DB divided by 2. AD equals to 9 over 4 units. DB equals to 4, all divided by 2. So we have here 9 over 4 plus 4. We multiplied 4 by 4 and then we divided by 4 in order to have a common factor with 9 over 4. And we got that 4 times 4 is 16, so 9 plus 16 over 4 over 2, it is equal to 9 plus 16 is 25 over 4 over 2. 4 times 2 is 8, so in conclusion we found out that R, the capital R, that is the radius of the big circle and the radius of the semicircles, it is equal to 25 over 8 units. Then we define the center of the big circle as point P here, and we define the center of the small circle as point Q, and we calculated the length of the short line segment DP. From the drawing, it is very easy to see that dP equals to dB minus PB. Again, dP equals to dB minus PB. Okay, dP equals to dB minus PB. dB equals to 4 units according to what is given us the question. What is PB? P is the center of the big circle. B is a point on the big circle itself. This is exactly the definition of a radius. So PB is the radius of the big circle that is equal to capital R. So we substituted PB by capital R and found out that dP equals to 4 minus capital R. But we have already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. We did it and we got that dP equals to 4 minus 25 over 8. So we have here 4 minus 25 over 8, so we multiplied 4 by 8 and then we divided by 8 in order to have a common factor with 25 over 8. So 4 times 8 is 32. 32 minus 25 divided by 8. 32 minus 25 is 7. In the denominator we have 8. So in conclusion, we found out that the short line segment dP equals to 7/8 units in its length. So we can write here that dP equals to 7/8 units in its length. Okay? Then we defined the point of tendency of tangent CD with this small circle as point O, and we defined the point of tendency of tangent DB with this small circle as point M. In the next step, we connected, we join together points Q and O by a straight line. What is the definition of line segment QO? Q is the center of the small circle. O is the point of the small circle itself. This is exactly the definition of a radius. So QO is the radius of the small circle, so we define the radius of the small circle as R. So here we know that QO is the radius of the small circle, and the radius of the small circle QO, it is drawn to the point of tendency. That is to say, it is drawn to point O, that is the point of tendency of tangent CD with this small circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent CD will be perpendicular to the radius OQ. So CD is perpendicular to OQ, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we join points Q and M together by a straight line. Q is the center of the small circle. M is a point on the small circle itself. This is the definition of a radius. So QM is the radius of the small circle that is equal to small r. And we have here the radius QM, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent DB with this small circle, and whenever we have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. So DB is perpendicular to MQ, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Then we focus on quadrilateral OQDM. In quadrilateral OQDM, we have 1, 2, 3 right angles. I'll repeat again. In quadrilateral OQDM, we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle OQM. In total, in total those 4 angles, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, we subtracted 270 degrees from this equation and found out that angle OQM, the missing angle, this missing angle OQM equals to 90 degrees. So actually in quadrilateral, inside quadrilateral OQDM, we have 4 right angles. Any quadrilateral that has 4 right angles must be at least a rectangle. So we relate to quadrilateral OQDM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, the opposite sides of a rectangle OQDM, they are equal to each other. That is to say, OQ must be equal to DM. Okay, OQ must be equal to DM. But we have already found out that OQ equals to small r. So we can write here that OQ equals to small r, and from this equation r equals to OQ equals to DM, we will derive that DM is also equals to r. So here DM equals to small r, that is the radius of the small circle. And then we found out the length of line segment PM. What is the length of line segment PM? PM equals to DM minus DP. Again, PM equals to DM minus DP. PM equals to DM minus DP. DM equals to R. Okay? And we have already found out that DP equals to 7/8. So in conclusion, we found out that PM equals to small r minus 7/8. Small r minus 7/8. Then here we have this point. In this point, those 2 circles, the small circle touches the big circle. This is the touching point of the big circle with the small circle, of the point of tendency of the 2 circles. And we can also define this point as, point S. Point S, it is also called as a launch point between the big circle and the small circle. The launch point, the touching point, the point of tendency, all those definitions are correct. And because of the fact that the small circle is located inside the big circle, this point S is defined as internal launch points. So in this drawing we have an internal launch point. Why? Because those two circles are touching each other internally. The small circle is located inside the big circle, and it touches the big circle internally. Then I presented to you rule number 2 that is related to internal launch points. According to rule number 2, if two circles have an internal launch between them, then the straight line that connects their centers passes through the launch point of the two circles. So as I've already explained to you, here point S is the internal launch point of the small circle with the big circle. So therefore we can implement rule number 2 in our drawing, because we have point S that is the internal launch point. Okay, and according to rule number 2, in the case that we have an internal launch point between two circles, then the straight line that connects their centers, that is to say P is the center of the big circle, Q is the center of the small circle. So the straight line PQ joins together the center of the big circle with the center of the small circle. And according to rule number 2, this straight line PQ, that just passes through the launch point of the two circles, that is actually point S. That is to say PQ passes through point S. That is to say PQS is one straight line. PQS is one straight line. We can say also that points P, Q and S, they are all located on the same straight line, or PQS is a straight line. Okay? Points from rule number 2 we will derive that points P, Q and S, they are all located on the same straight line, or PQS is one straight line. Okay? Then we found out what is the length of line segment QS. Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. That is to say QS is the radius of the small circle that is equal to small r. What is the definition of line segment PS? P is the center of the big circle. S is a point on the big circle itself. This is exactly the definition of a radius. So PS is the radius of the big circle that is equal to capital R. But we have already found out that capital R equals to 25/8. Okay, so in conclusion, PS equals to capital R, and it is equal to 25/8 units in its length. Then we found out the length of line segment PQ. From the drawing, it is very easy to see that PQ equals to PS minus QS. Again, PS minus QS equals to PQ. Here, PQ equals to PS minus QS. So PQ equals to PS. We already found out that PS equals to capital R, so we can substitute PS by capital R. And we already found out that QS equals to small r. We can substitute QS by small r. So in conclusion, we found out that PQ equals to capital R minus small r. But we have already found out that capital R equals to 25/8. So we can substitute capital R by 25/8. We did it, and we found out in conclusion that PQ, line segment PQ equals to 25/8 minus small r. Okay? Then I copied the right green triangle PQM in a new page, and we implemented the Pythagoras theorem in the right green triangle PQM. In the right green triangle PQM, we know that the hypotenuse equals to 25/8 minus small r. Side QM equals to small r, it is the radius of the small circle, and side PM equals to capital R minus 7/8. Okay? We implemented the Pythagoras theorem on this right triangle PQM. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. the hypotenuse is PQ, so the square of the hypotenuse is PQ square, and it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to QM square plus PM square. So PQ equals to 25 over 8 minus R, so we substitute PQ by 25 over 8 minus R. If we square it, we will get PQ square. QM equals to R, so QM square equals to R square. PM equals to R minus 7/8, so if we square it, we get PM square. We open the brackets on both sides of equation number 1. Here 25 over 8 minus R square equals to, according to the geometric identity, that A plus B, A minus B square equals to A square plus B square minus 2 times AB. We will get it 25 over 8 minus R square equals to 25 over 8 square. 25 over 8 square equals to 25 square, that is 625, over 8 square, that is 64, plus R square minus 2 times 25 over 8 times R. And it is equal to R square plus R minus 7/8 square. R minus 7/8 square equals to R square plus 7/8 square is 7 square, that is 49, over 8 square, that is 64. So in conclusion 7/8 square equals to 49 over 64 minus 2 times R times 7/8. So here we have R square on both sides of the equation number 1, so R square will get cancelled. And what is left from equation number 1 after we cancel R square? What is left? It is actually 625 over 64 minus, here we have minus 2 times 25R over 8. We divided both the numerator and the denominator of this expression by 2. 2 over 2 is minus 1, so 2 will get cancelled. And in the denominator of this expression, we have in total minus 25R in the numerator. And in the denominator, we have 8 over 2, that is 4. So in conclusion, this expression equals, after we divide it by 2, it is equal to minus 25R over 4. And it is equal to R square plus 49 over 64. Here we have minus 2R times 7/8 times 7 over 8. We divided both the numerator and the denominator of this expression by 2. So minus 2 over 2 is minus 1, so minus 2 will get cancelled. So in the numerator we left only with minus 7R. In the denominator we have 8 over 2, that is 4. So in conclusion, this expression, after we divide it by 2, equals to minus 7R over 4. Then we multiply this equation number 1 by 64. So here 64 over 64 is 1, so we left only with 625. And we have here minus 64 over 4 is minus 16. So in conclusion, in total this expression equals to minus 16 times 25R. And it is equal to R, 64 times R square is 64R square. 64 over 64 is 1, so we left only with 49 here. And minus 7R over 4 times 64 is minus 64 over 4 is minus 16. So in conclusion, this expression equals to minus 16 times 7R after we multiply it by 64. After we multiply it by 64, this expression minus 7R over 4 equals to minus 16 times 7R. So here we have, according to equation number 1, 625 minus 16 times 25R equals to minus 400R. And this is equal to 64R square plus 49 minus 16 times 7R is minus 112R. Okay, then we added 400R to this equation, equation number 1. So we have here 625, 400R minus 400R is 0, and we have here 64R square plus 49, and 400R minus 112R, it is plus 288R. So in conclusion, we found out that according to equation number 1, 625 equals to 64R square plus 49 plus 288r. We subtracted 625 from this equation number 1, and we found out that 625 minus 625 is 0. And here we have 64r squared plus 288r, and 49 minus 625 equals to minus 576. So in conclusion, according to equation number 1, we found out that 0 equals to 64r squared plus 288 minus 576. Here we divided this equation number 1 by 32. 64 over 32 is 2, so in conclusion, in total this expression equals to 2r squared. 288r over 32 is 9r, and minus 576 over 32 equals to minus 18. So in conclusion, we got this quadratic equation. According to equation number 1, we have the quadratic equation 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18. And the variable that we are looking for in this quadratic equation is r, so x equals to r. Okay? And the general formula for solving out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Here, a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is r, so x equals to r. So we'll substitute x by r, and we'll put the data inside this general formula for solving out the quadratic equation, and we'll find out the value of the values of r, that is the radius of the small circle. So r equals to minus b, b equals to minus 9, so minus b is minus 9, plus minus square root of b squared. B equals to 9, so 9 squared is 81. Minus 4 times a times c. Minus 4 times a is 2, and c is minus 18. All divided by 2a. A is 2, so 2 times 2 is 4. So we found out that r equals to minus 9 plus minus, inside the root we have minus 4 times 2 is minus 8. Minus 8 times minus 18 is plus 144. So in conclusion, we found out that inside the root we have left only with 81 plus 144 divided by 4. 81 plus 144 is 225. So in conclusion, we found out that r equals to minus 9 plus minus square root of 225 over 4. The square root of 225 is 15. So here we will have two solutions that are possible for r. The first solution is that r equals to, first of all, we have r equals to minus 9 plus minus 15 over 4. So here we have two solutions that are possible for r. The first solution for r is r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that r is a negative number, that is to say it is equal to minus 6. But r, according to our definition, is the length of the radius of the small circle. So r is the length of the radius of the small circle, and r is a length, it must be a positive number. It can never be equal to minus 6, that is a negative number. So we cancel this solution, and we left only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, and r equals to 6 over 4. We divided both the numerator and the denominator of 6 over 4 by 2. 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, we found out that r, the radius of the small circle, equals to either 3 half units, or in terms of numbers, it is equal to 1.5 units. I repeat again, r, that is the radius of this small circle, equals to either 3 half units, or in terms of numbers, it is equal to 1.5 units. Okay, thank you very much.